Section 4, Part B. So we've talked about outcomes, we've talked about events, we've talked about sample spaces of random phenomena. Now we want to talk about every event having a probability. Every event, everything, so you can think of the outcomes as the individual separate little things that can occur when you do the random phenomenon. And then you can think of an event as something that can happen, not necessarily as distinct from something else that can happen. So everything that can happen when you do the random phenomenon has a proportion of times it would occur in the long run. Now, you can't occur less than all the time, and try again. You can't occur less than none of the time, and you can't occur more than all the time. So the proportion of times it would occur in the long run is always between 0 and 1, inclusive. Now we've got to be very careful about 0 and 1, and we'll talk about that in point 2. But certainly the probability can't be more than 1. It can't occur more than all the time. And it can't be less than 0. It can't be negative because it can't occur less than none of the time. So the probability of any event is between 0 and 1. You do have to be a little careful, however, and that is point 2. Now let's think about this. An event happens if the outcome that occurs is in its set. The sample space itself is the set of all possible outcomes. So by definition, event S, the sample space itself, happens. By definition, event S, the sample space, by definition, the event that you get, the outcome that you get is in the set that has all possible outcomes in it. Not to be too blunt about it, S happens. This time, the next time, every time. S always happens. And since S always happens, it occurs 100% of the time in the long run. To put it mildly, sound familiar? So the probability of the sample space itself is 1. The sample space is the event something happens. Yes, for sure. Every single time. At the other end of things, the empty set, which is technically a subset of the sample space, it's the set with nothing in it. Pick your favorite notation for the empty set. The set that contains no outcomes. By definition, this event cannot possibly happen, right? By definition, the outcome that you get cannot be in the set that has nothing in it. So the empty set is the impossible event. It doesn't happen next time. It doesn't happen the time after that. It never happens. It is the idea of nothing happening, and that never happens. Something always happens. As a sample space has probability 1. Nothing never happens. It is never the case that nothing happens. So if it doesn't happen next time, if it doesn't happen the time after that, if it never happens, then to put it mildly, it has probability 0. S is the certain event. The empty set is the impossible event. Now, before we jump to any conclusions about the or equal to's here, remember we've seen examples that are a bit more subtle than this. Having probability 0 does not necessarily make something impossible, and having probability 1 does not necessarily make something certain. Let's think about our infinitely sharp spinner again that could land at any real number between 0 and 4. The probability of it landing at any particular number, a rectangle which was 0 wide and don't care high, had area 0. The probability of any particular number is 0, but it's going to land somewhere, right? In our infinitely sharp spinner, the probability of a 2, for instance, 2.0 repeating, the probability of that was 0, but that didn't make it impossible. We could say that about any number, and it's going to land somewhere, right? So having especially when there's an infinite number of things in your sample space. In the case of the spinner, an infinite number of dots, an infinite number of places on that spinner it could land, then yeah, having probability 0 doesn't necessarily make it impossible. It only makes it infinitely unlikely, at least. Okay? At the other end of things, there is probability 1 that you'll get, and when we spin our spinner, there's probability 1 that you'll get something other than 2.0 repeating, right? Less than 2, a half. More than 2, a half. A half plus a half, 1. So less than 2 or more than 2, that is to say not 2, a half plus a half, 1. 2 rectangles, each with area a half, right? So, or put it another way, the entire rectangle, take away the area in that line at 2 is still got area 1. So if something has probability 1, it's not necessarily certain, it's just infinitely likely. So we do have to be a little bit careful. Now these distinctions don't make any sense when your sample space has got 6 things in it. But again, when there's an infinite number of things in your sample space, you have to be a little bit careful. The other example that we did was flipping the coin, right? We'll talk more about this when we talk about rule number 5 here. But the bottom line is that the probability that a fair coin lands head, 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 head is a half times a half times a half times a half times a half. Now, if you multiply halves forever, and you do have to be a little careful about what you mean, but let's put it this way, if you multiply a billion halves together, you're going to get something very close to 0, and so on and so on. So the probability of a fair coin landing heads forever is a half times a half times a half times a half times a half forever, which is mathematically 0, can be proven. But again, that doesn't make it impossible that a coin could land heads forever, only infinitely unlikely. We're not going to talk too much about things like that in this course, an infinite number of repeats, but I'm just illustrating the principle that there's a difference between infinitely unlikely and impossible. It is impossible for the coin to land unicorn. It is infinitely unlikely for the coin to land heads forever and ever and ever. Fair enough? The probability of the certain event is 1, but not necessarily, the probability of something that's certain is 1, but not necessarily the other way around. The probability of something that's impossible is 0, but not necessarily the other way around. Another principle we've used in the past, the probability that something doesn't happen is 1 minus the probability it does. Well, obviously, one of two things is the case for any event. No more, no less. It happens, it doesn't. Put them together and they've got to add up to everything, right? So the probability that something doesn't happen is 1 minus the probability that it does. The probability that the coin doesn't land heads is 1 minus the probability that the coin lands heads. Now that is true regardless of how sarcastic you are, right? It may not necessarily be true that not being heads makes you a tail. But one thing's for sure, either it's a head or it's not a head. As sarcastic as you like, it's either a head or it's not a head. It's either whatever outcomes constitute A, or it's all of the remaining outcomes. And together they constitute everything. We've used this principle before, right? Just not necessarily from a probability perspective, right? In section 3, the probability that you're to the right is 1 minus the probability you're to the left. The probability that it's not to the left is 1 minus the probability that it is to the left. We've done that in our area pictures, in our normal pictures. We did it again with our uniform distribution, right? We did it, I can't easily call it up here, but you remember the picture where we had the red and the white and the blue shaded areas. And we said that you could either think of the white as just the white area, or you could think of it as 1 minus the red and blue areas. Now we get to the interesting ones. Rule number 4. The probability of A or B is the probability of A plus B sometimes. Or means add sometimes. But when? Well, let's think of a couple of examples. Let's take, which ones am I doing here? A and D. So the coin lands odd, the coin lands 2 or 4. So what is the probability that the coin lands odd or 2 or 4? A or D? Odd or 2 or 4? Well, let's think it through. Let's say that you're talking about the die. Let's say that you're talking about a fair die. And more on this a bit later, but let's take it for granted that if you have a fair die, then the probability of any particular one of these is a sixth. Or at least that they're all equally likely. So if we're talking about 3 out of 6 possibilities, then the probability of this is 3 out of 6 equally likely things. The probability of A is 3/6, right? 2 out of 6 equally likely things. The probability of D is 2/6. Now, these probability rules are true when they're obvious and they're true when they're not. They're true when your sample space is this full stop, and they're true when your sample space is an infinity of dots. They're true for weird sample spaces, they're true for nice ones, but for nice ones, where you can actually list off the different things that can happen, you can think of probability this way. You can think of every outcome as having a little number attached to it. In our case, a sixth, a sixth, a sixth, a sixth, a sixth, a sixth, and you just add them up. On the outcome level, you can always add probabilities. It's only overlap you have to be a little careful of, and outcomes, remember, never overlap. Being one means not being another. So for instance, if you want to talk about odd or 2 or 4, then you can notice that the probability of odd is 3/6. The probability of 2 or 4 is 2/6. Which is what I'm doing here. And if you do it longhand, odd or 2 or 4. Now, or, remember, in the set theory sense means union. Odd or 2 or 4 means that it happens if you get a 1, it happens if you get a 3, it happens if you get a 5, it happens if you get a 2, it happens if you get a 4. In other words, we're unioning the sets. All of these outcomes, 1, 3, 5, 2, 4, that's the set A or D, a union D. So A or D, odd or 2 or 4, means the set 1, 3, 5, 2, 4. Remember, sets have no order and they have no repeats. So I don't care what order you list those in, 1, 3, 5, 2, 4. And that set obviously has 5 out of 6 for a fair die equally likely things. So brute force tells you that it's got probability 5/6. 5 out of 6 equally likely things. And sure enough, it is 3/6 plus 2/6. So here's an example of where the principle works. Or let's do it here. On the left, we're doing it the longhand way by making the set in question. On the right, we're using the shortcut from the two more easily computed probabilities. And sure enough, the highlight, they're equal. The reason it works is because, remember, sets have no repeats in them, but nobody was going to get double counted. If A and B have no outcomes in common, then or means add. If there's nothing that's in both of them. In set theory terms, we say that the sets are disjoint, that their intersection is empty, that there's nothing that's in both. Now remember, something that is in both could be a little bit complicated. Remember our pictures of the random spinner from 0 to 4. where we said, I forget what the numbers were, but something like more than a half or less than 2.5. You have an infinite number of dots between a half and 2.5, which were being shaded in twice, which were being double counted. That's the kind of thing you want to avoid. Less than a half or more than 2.5, nothing got double shaded. It couldn't be both. You can add those. But less than 2.5 or more than a half, you had that whole purple looking region that was shaded red and blue. Remember that? All of those dots, an infinite number of dots, that whole territory from underneath the purple rectangle, an infinite number of dots are in both sets. So you can have easy examples, you can have hard examples, but if there's nothing that's in both sets, then the principle will work. In set theory terms, disjoint sets. In happenstance terms, mutually exclusive events. One happening means the other could not possibly have happened. They mean the same thing. Set theory, happenstance. Die landing odd happening means it couldn't possibly be event D, right? And event D, getting a 2 or a 4, means it couldn't possibly be the case that the die lands odd. Each of them happening excludes the possibility of the other happening. Mutually exclusive. Contrast, an example where the principle fails. Even or prime. Even, 3 equally likely possibilities out of 6, 3/6. Prime, also 3 equally likely possibilities out of 6, also 3/6. So the probability of even is 3/6, and the probability of prime is 3/6. What about even? So that's what's going on over here. If you add them, probability of B plus the probability of C, you get 6/6. What about B or C longhand? Well, again, or means union. Or means create the set which is composed of all the things that are in at least one of the sets, right? So what are we talking about? B or D, right? No, B or C. So if we make the set, remember, sets have no repeats. 2 is in there, 4 is in there, 6 is in there. I said 2, 3 is in there, 5 is in there. 2, 4, 6, 3, 5. You don't count 2 twice. Sets have no sense of repeats. There are no repeats in sets. And again, the order doesn't matter. So 2, 4, 6, 3, 5. 5 equally, well, for fair die, equally likely possibilities out of 6. That's pretty conclusive. If it's a fair die, then 5 equally likely possibilities out of 6. So over here on the left, we have the long way of finding the probability of B or C by actually creating the set B or C, B union C. And over here we have the shortcut, which doesn't work. And the reason it doesn't work is because they weren't disjoint. On the atomic level, you're adding in the probability of a 2, the probability of a 4, the probability of a 6, the probability of a 2 again, the probability of a 3, the probability of 5. It's going to be too big. And it's going to be precisely too big by what you've double counted, right? A 6th plus a 6th plus a 6th plus a 6th we've already counted, plus a 6th plus a 6th. It's going to be 1/6 too big. And that is exactly what we're seeing. Right answer, 5/6. Wrong answer, 1/6 too big, because we double counted the probability of 2. Sets have no concept of order or repetition. Like we said with the shaded purple territory, which was blue on top of red, you don't get extra credit for satisfying both conditions. Event B or C happens if event B happens. Event B or C happens if event C happens. Event B or C happens if you get a 2. That means both happen. But it doesn't make it any more true. You don't count it twice. And this is what I was just saying a minute ago, right? We saw something similar in our spinner example. I may not have used the same numbers, but less than 3 or greater than 1 we'll double count that whole territory from if you shade in everything less than 3 and you shade in everything greater than 1, then you're going to shade in that territory from 1 to 3 twice, and you don't want to double count that. The principle's the same. Again, notice that for something like that, you kind of have to use area to represent probability, whether it's rectangular shape or bell-shaped, whatever shape. But for simple examples, this or this or this or this or this full stop happens, you can think about things on the atomic level, but regardless of how you think about it, you don't want to double count the things that are in there twice. So there's easy examples, there's more complicated examples, but the probability principles are always true. Point number 5. People often get 4 and 5 mixed up because they diagram similarly, but they could not have less in common. Or means add sometimes, and means multiply sometimes. Now, if you've taken this before or done anything more sophisticated, I should point out that this is all we're going to talk about here. There is another version of this principle where you subtract off the intersection, you subtract off what you've double counted, add it in again, subtract it off to get rid of the double counting. We're not going to get into it that deeply if you've seen that before, because we don't really need it for where we're going. Remember, everything we're reviewing here everything we're talking about in these sections, we're only doing so that the stuff in the later sections will make sense. So these are the simple versions of these principles. We're not going to deal with the more complicated ones. Likewise, there's a more complicated version of this involving conditional probability, which we're not going to get into. This is good enough for us. And means multiply sometimes, or means add sometimes. That is where the similarities end. Other than that, they could not have less in common. If A and B are independent, that is a cut and paste error. Ignore the purple entirely. If A and B are independent, ignore the purple, it's a cut and paste error. If A and B are independent, then and means multiply. Independent events means knowing, I'm going to make a note of that so I can put these corrections someplace in the future. Okay, and there was another one that I forgot to make a note about, but you'll find it. So ignore the purple, it's a cut and paste error. A and B are independent, then the probability, then and means multiply. Probability of A and B is the probability of A times the probability of B. What are independent events? There's different ways you can define this, but the simplest is to say that knowing that A has occurred does not change the probability of B and vice versa. So in other words, two events are independent if knowing that one of them has occurred does not shed any insight whatsoever into whether the other has occurred. It does not make it more likely. It does not make it less likely. It doesn't give you any additional insight whatsoever. For instance, whether the first flip of the coin being heads and second flip of the coin being heads are independent. Because if you pick it up and give it a good shake, then whether the first flip of the coin was head or not doesn't give you any insight into whether the second flip is a head. But on the other hand, let's look back up here, at our sum of two dice. If you know that the first roll was a 1, that you're in this territory, then that cuts down to 0 the probability that the sum is 12, for instance, right? So let's think about that. If you don't know anything, then the probability of a 4, let's say, is 1, 2, 3 equally likely outcomes out of 36. The equally likely part will present itself, as I said. But if you take my word for it that these are 36 equally likely outcomes, then then the probability that they add up to 4 is 1, 2, that is 2 comma 2, 3, 3/36, right? On the other hand, if you know that the first die was a 1, then there are now 6 equally likely outcomes, right? 1 plus 1, 1 plus 2, 1 plus 3, 1 plus 4, 1 plus 5, 1 plus 6. And it's the third one, right? 1 plus 3. 1 out of 6 equally likely outcomes. So knowing that the first die was a 1 changes the probability of a sum of 4. It changes it from 3/36 to 1/6. Knowing that the first roll was a 1 changes the probability that they add up to 11, changes it to nothing. Knowing that the first roll was a 6 changes the probability that the dice add up to 3 to nothing, right? And so forth and so on. Doesn't have to make it impossible, it only has to change it. So obviously, knowing what number the first roll of the die happens to be changes it from something like this to 6 equally likely possibilities, right? Number plus 1, number plus 2, number plus 3, number plus 4, number plus 5, number plus 6. So failure to be independent doesn't necessarily mean that knowing that A has occurred tells you the probability, tells you whether B has occurred, but it does shed some insight into it. If two events are independent if they have absolutely nothing to do with one another. Now let's think about that for a second. Either it is the case that two events have absolutely nothing to do with one another, in which case you can use this principle, or it is not the case that the two events have absolutely nothing to do with one another, in which case you can't use the principle. Now again, we've seen different examples of the way this can play out. If they are dependent, if it is not the case that they have nothing to do with one another, then knowing that A has occurred can shed partial insight. It can change the probability of B from 3/36 to 1/6 and so forth and so on, or it can completely tell you whether that B has occurred or not in other situations. Does a coin land heads? Does that same coin land tails? Well, A, coin lands heads. B, coin lands tails. Knowing whether A has occurred completely and utterly tells you whether B has occurred. That's the opposite extreme from independence. If two things are dependent, then they can completely and utterly determine one another, or they can just change the rules slightly to give you partial insight. Independence means no insight whatsoever. Failure to have no insight whatsoever leaves open a whole world of stuff. Completely determining one another, slightly affecting one another, but things are either independent or they're not. If they're independent, then we can multiply for and. If they're not independent, we can't. Now, this is to say we need to know the context of B. I don't want to get off into a digression about conditional probability, but it is important to understand that we have to know the probability of B in order for this principle to make sense. And if there's interplay going on here, if the probability of B is not even a well-defined thing, if it depends on what's going on with A, then you can't really use this principle, right? Because there is no probability of B. You need to have, in some sense, that probability of B regardless of what's going on with A in order to use this principle. So if they're interdependent, then the probability of B is not even going to be a thing. A specific thing. It could change. And I'll show you what I mean with that in some examples. Consider the similarity and differences between the following three examples. Example 5a. Flip a fair coin twice. I haven't been counting, but I'm assuming this is example 5. Example 5a. Flip a fair coin twice. What's the probability of getting a head followed by a head? Well, it's not that complicated as we said. We talked a little bit about it, but let's do it from scratch here. Let's let A represent the event that the first flip is ahead. Pick up the coin, give it a good shake, flip it again. B represent the probability that the second flip is ahead. Well, the probability that the first flip is ahead is a half. Pick it up, give it a good shake. What the first flip was totally irrelevant. The probability of the second flip being ahead is a half. If the coin landed heads and you pick it up and you start to shake it, the probability of the second coin landing heads is a half. If the coin landed tails and you pick it up and you start to shake it, the probability of the next flip being head is still a half. If the coin landed on the floor while your eyes were closed and you feel around for it with your eyes still closed, pick it up and give it a good shake so that you have no idea whether the first flip was ahead or not, the probability of the next, you're still shaking, the probability of the second flip being head is still a half. It is literally irrelevant. If you know that A occurred, this is a half. The shaded is a half. If you know that A didn't occur, this is a half. If you don't have any idea whether A occurred, this is still a half. The probability of the second flip being ahead is a half, whether the first flip was a head or tail or whether we didn't notice one way or the other. They're independent. The first flip being ahead sheds absolutely no insight into whether the second flip is ahead. They're independent. They don't affect, the probabilities don't affect each other in any way. So and means multiply. A and B, of course, is both flips are ahead. The probability that you get two heads in a row is the probability that the first flip is ahead times the probability the second flip is ahead. Half times a half, a fourth. Now you could say all the same thing about tail and so forth and so on. So, any particular one of these is going to be a fourth. Or you could use an argument from symmetry. There's nothing you can say about a head that you can't say about a tail for a fair coin. So obviously there are four equally likely outcomes. Example 2. Standard deck of cards. 26 red cards, 26 black cards. No jokers, no Harvey Dents, just give it a good shuffle. What is the probability of getting a red card followed by a red card? Now let me just say that for the purposes of this, I'm not particularly interested in the answer. I only want to illustrate the principles involved here. So A is the event that the first card is a red. Now half the cards are red. Well, 26 divided by 52. They're all shuffled together. So you've got a 1/2 chance. You've got 26 equally likely cards out of 52 cards. 26 out of 52 equally likely cards. 1/2 the cards are red. You've got a 1/2 chance of getting a red card the first time, whether you call it a half or 26 out of 52. Now, if I put the card back and give it a good shuffle, then it is pretty much identical to the previous problem, right? So that's not what I mean. I mean, keep the card out. Take that first card out, put it to one side, shuffle them or don't, they're already shuffled. Pick the second card. Having taken out that first card, pick that second card without replacement. Pick that second card. What is the probability that the second card is red? You can see it's not such an easy question. It literally depends on what the deck looks like at this point. It literally depends on what you took out. In other words, the probability of B literally depends on whether A happened. So here, A and B are dependent. Here, A and B are not independent, and the and multiply principle will not work per se. So you can see that the probability of B is not even a well-defined thing. Either the first card is red or the first card is not red. It's black. And there's a 1/2 chance you go down either route. But then that will put you into one of two universes, right? In either universe, there are 51 cards left in the deck. But if you have not taken out one of the red ones, then there are still 26 red ones. And if you have taken out one of the red ones, there are now 25 red ones. There's two things to say about these numbers. One is a little bit more obvious than the other. Can we concede from, without a calculator, can we concede that some number of 51sts is not the same as some other number of 51sts? This is about 490196 something, and this is about 0.5098 something, 0.5098039 something. So let's call this one 4902, and let's call this one 5098. 0.4902, 0.5098. They are different. They are different numbers. So the probability of B does change based on whether or not A occurred. Again, I don't want to get off into a digression on conditional probability, but the point is that the probability of B in the abstract sense is not even a thing, right? It literally changes. It's not always the same number. It depends. It's not a specific thing. It's context driven. It depends on where you stand at that point. Now the answer to our question is you multiply down the path. I'm not really interested in that because it takes us a little too far afield for reasons we'll see shortly. But the answer to the question, what is the probability of getting a red card followed by a red card? Well, number one, you've got to go down the top path, right? So the answer would be 1/2 times 25 over 51. If you find yourself here, then you already know the answer. It's not a red card followed by anything. So you've got to go down the top path. It's 1/2 times 25 over 51. The answer does not interest me because I'm not really getting off into a digression on conditional probability. I'm not really interested in these tree diagrams. And why I'm not interested in these tree diagrams for the long run, we'll see as we do our next example. The point is, probability gets very complicated if what you're about to do depends on what you've already done. This is not something we want to think about in this course. Probability is very complicated if you've got to work in these tree diagrams, bearing in mind this is the simplest possible example. Two things followed by two things. So we don't necessarily want to be thinking about this. It's just an illustration of where the principle doesn't work because you don't have the independence. It's not even that the principle doesn't work per se, it's that there is no such guy as the probability of B. It literally changes based on where you stand at the time, right? So you do have to be very, very careful. Point is that they're not independent, so the principle doesn't even make sense, really. Never mind it working. Now so there's two things to say about these numbers, as I said. The obvious one is that they're different. The less obvious one is that they're not that different. Now that's neither here nor there. They are different. So the probability of B literally changes numbers. It goes from one number to a different number. A and B are not independent. On the other hand, they're not that different, right? They're both about 1/2. So taking one card out of the deck doesn't greatly change the rules, but it does change them. A and B are not independent. It makes everything more complicated. It gets into these tree diagrams that we don't want to be thinking about. Now, with all that in mind, let's take example 5C. And what I want you to do is I want you to think about whether it's more like the first example, 5A, or more like the one we've just done, 5B. Let's take 100 decks of cards and shuffle them together. 2,600 red cards and 2,600 black cards. Same question. What is the probability of a red card followed by a red card? Or shall we say the scenario of getting a red card followed by a red card? Same rules. A, the first card is red. B, the second card is red. Same idea of without replacement. So you keep the card to one side. So 2,600 out of 5,200, half the cards are red, right? So the probability of the first card being red is 1/2. Now, either the first card was red or the first card was not red. And there's a 1/2 chance of going down either of those routes, right? What does the deck look like at this point? Well, in either universe, There's 5199, one less than 5200. There's 5199 cards remaining. If you have not taken out one of the red ones, then there's 2600 red ones left. If you have taken out one of the red ones, then there's 2599 red ones left. Now again, without computing numbers, is it obvious that some number of 5199ths is not the same as some other number of 5199ths? So once again, A and B are not independent. The probability of B obviously changes based on whether or not A has occurred. And so once again, this principle is not going to make any sense, because the probability of B doesn't rise to the level of being a thing. It literally depends on where you stand at that point, which universe you're in. So, well, the answer to our question, as before, is it's 1/2 times this, but that's not what I'm interested in. Let's look at the numbers. A and B are not independent, therefore, all I'm trying to do is a discussion of independence. A and B are not independent. However, let's run the numbers. 2599 over 5199, 2600 over 5199. I need a lot of decimal places here to make my point. This is 0.499904. This is 0.500096. For all practical intents and purposes, these are both a half, right? So as you might have suspected in the first place, taking one card away from thousands of cards didn't really change what remained, right? Before we took that one card away from 5200, half of them were red. After we took that card away, whether it was red or not, it's still the case that about half of them are red, right? Taking one card away from 5,000 cards doesn't really change to any degree that a sane human being has to really concern themselves with the fact that half the cards are red and half the cards are black, right? So regardless of which universe you find yourself in, the probability of B is still close enough to a half. In the real world, there is this magical thing called close enough. A and B are not technically independent. These are different numbers, but they're not that different. They're not different enough for us to care about. Here they were noticeably different, or kind of borderline. But here they are not remotely different, right? So for all practical intents and purposes, they're independent. They are close enough to being independent. Now we'll talk about what. Don't worry yet in the course about what is close enough and what isn't. We'll worry about all these points later. The point here is just to take a very obvious example of where taking one card away doesn't really change the fact that half of what's left is red. What you're taking away is negligible. What you're taking away is just not enough to change the rules noticeably, significantly, to any degree that we need ever concern ourselves with. That's a half, that's a half. You might almost say that here, but maybe not quite. But certainly down here, these are both basically a half, close enough. Taking the first card away does not change the content of the deck to any noticeable degree. The rules are effectively the same the second time as they are the first, no matter what happens the first time. In practice, it's really more like flipping the coin twice, where it literally didn't change the rules at all. It was close enough to being like the first example. It was, on the face of things, more like the second example. Why is this important? Because in the real world, if you want to know what proportion of, what example am I doing here? Left-handedness in New York. In the real world, if you want to know what proportion of people in New York are left-handed, then you don't ask 5 people. You ask 5,000 people. Why don't you ask everybody in New York whether they're left-handed? If you want to know what proportion of people in New York are left-handed, why not just ask everybody in New York State whether they're left-handed? Obvious answer, you can't. So that's a non-starter. You poll. You take a poll, preferably a large-sized poll, we'll worry about that later, and you look at the results, right? So now bear in mind, if you could ask a noticeable chunk of everybody in New York State whether they were left-handed, let's say you could ask 10% of the people in New York State whether they were left-handed. Well, get 9 friends to help you. Ask everybody. It's not that much harder. You can't. You can't ask everybody in New York State. You can't ask 10% of the people in New York State. There's, what, hundreds of millions of people in New York State, tens of millions at least. You can't ask 10% of the people in New York State whether they're left-handed. You can't ask 1% of the people in New York State whether they're left-handed. You can't ask any noticeable percentage whatsoever of the people in New York State whether they're left-handed. So you see, it's not like taking cards out of a deck. It's like taking cards out of 100 decks shuffled together. In the real world, the poll, let's say you ask 1,000 people in New York State whether they're left-handed. That's still nothing compared to the tens or hundreds of millions of people in New York State, right? Even if you take away 999 left-handed people, even if by sheer weird cosmic fluke you happen to get 999 left-handed people when you look at them in New York State out of tens or hundreds of millions, you're still taking away practically nothing, right? 10% of tens of millions, 90% of tens of millions. With room to spare, you could get 1,000 left-handed people. You could get millions of left-handed people, right? So taking 1,000, taking 999 left-handed people away from tens or hundreds of millions, you're still taking away approximately nothing, right? It's still true that about 10% of people in New York State are left-handed. So the chance of getting a left-hander the 1,000th time is still close enough to 10%. Worst case scenario, you get 999 left-handed people in a row, and now maybe you're down to 9.99999% left-handed people, right? Or other worst case scenario, you get 999 right-handed people in a row. So now the left-handers are slightly higher in what's remaining in the population, right? So maybe it's 10.00001%. Who cares? It's 10%, right? This is why we don't have to worry about tree diagrams. Remember, these are the practical things we do in statistics. This is the beauty of it. The reason that we are polling in the first place, rather than asking everybody in New York State whether they're left-handed, is because we have to. We can't ask everybody in the state. We can't ask 10%. We can't ask 1%. We cannot ask any noticeable chunk of people in the state whether they're left-handed. The fact that we're asking 1,000 random New Yorkers rather than tens or hundreds of millions, doing that implies that the 1,000 is insignificant compared to the population of New York, right? We wouldn't be doing it otherwise. We pick 1,000 people rather than tens of millions because 1,000 is manageable, tens of millions is not. No noticeable fraction of tens of millions is doable. The 1,000 people may be a lot of people, but it's negligible compared to what's out there in New York. So it's really like taking 2 cards out of hundreds of cards, right? 1 or 2 cards out of 5,200 are not going to be missed. Half red, half black. 1,000 or 999 people, let's say, if we're about to do the 1,000th, 999 people taken away from New York State and put to one side are not going to be missed. you still have, let's say 10% of people in New York are left-handed. You're still basically true, right? 999 people from tens of millions put to one side are not really going to change that. They don't make any noticeable dent. That's the beauty of it. In the real world, we are doing this. The entire reason we're doing this is because what we look at is insignificant to compared to what we would like to look at, and therefore, because it is insignificant, we have close enough to independence. So for practical applications in statistics down the line, we always have close enough to independence. If it is not technically true that you're using the identical rules over and over and over, like when you flip the coin, then it is close enough to being true that you are using the identical rules over and over and over, because the people you are taking away with replacement, without replacement, it doesn't matter. The people that you are taking away are insignificant compared to what's out there. The only way this could go wrong is if you were asking a noticeable chunk of everybody in New York whether they were left-handed, because then you're taking away enough to change the balance of what's out there, right? But you never would be, because you can't. That's why we're sampling in the first place. Samples are insignificant compared to what's out there. What we're polling, the number of people or things that we're polling, are insignificant compared to what we're polling from. That's why we're polling. So we're always in situation 3 at worst. We're always in the situation of where we're close enough to having the same rules every time we pick. Probability is a lot simpler if it's the same rules applied over and over and you can just multiply them. A half times a half, a tenth times a tenth, whatever. And it's incredibly complicated if you've got to use tree diagrams. You could never do anything like this type of analysis down here, which we'll talk about later in the course. Well, you could never do anything like this type of analysis if you had to do a tree diagram with 999 levels. Try 2 to the 1,000 on your calculator and see what happens, but it won't be pretty, and that's only the number of levels of the problem, not the problem itself. Probability statistics would be impossible if we had to use these tree diagrams, but that is the beauty of it. What we are looking at is insignificant compared to what's out there, so effectively we have close enough to independence, close enough to the same rules applying the first time you look at a person, second time you pick a person. Because what we're picking is insignificant, if there's a 10% chance, if 10% of the people in the state are left-handed, then there's a 10% chance the first one will be left-handed. Put them back or don't, and there's close enough to being a 10% chance the next time you pick, at the 1,000th time you pick. Get to half the people in the state, yeah, you're starting to get problems, but that's the beauty of it. You never get to that point, because that's why you're polling in the first place. So 5C is a look into the future. 5C and its implications give you an idea of why we're interested in probability. Remember, the goal is not to do probability just because I'm being sadistic here. The goal is to do probability because it will be handy for what we want to talk about later. And this purple highlight, this example 5C and the consequences of it, we'll talk about it in more detail much later in the course. It's a look into the future. But this is the kind of scenario we'll be in. So you never really in this course have to worry about not having the independence. Now, one last word on this for the next section. This can play out in all kinds of ways, but as you've begun to see from these examples, what we're interested in with the independence is repeat performances. First card read, second card read. First person left-handed, second person left-handed. That's the way we're going to use these principles. And for all practical intents and purposes in this course, we always have that independence going for us. So that if it's not true that we've got exactly the same rules first, second, third time we do something, then as with the cards, it is, as with the 5200 cards, it is close enough to being true that we have the same rules each and every time we do something. And that enables you to use the multiply principle. How that plays out, you can check out in the practice problems number 4, number 2 in section 4. This is a particularly good one. The others are more basic. This is a very good one to practice because it's got a little bit of everything. The other problems here are much more basic, but this one gives you a decent idea of the kind of thing that we're going to be doing in the next section. So it's a very good one to practice on, picking 4 marbles out of a vat and basically having the same rules every time you pick. It's very closely related to what we were just talking about. So it's a very good practice problem to check out before we go on into section 5, where we'll effectively be doing a lot more of the same. For change, section 5 is a direct continuation of section 4. We will be taking the probability principles, and we're going to focus them a little less on abstract probability and a little basic abstract probability, and a little bit more on why we're interested in probability. So we're going to take the principles in the last section and we're going to bring them a little bit more into focus. 5 will be a direct continuation of 6. 5 will be a direct continuation of 4, and 6 is going to be just kind of a series of PS's, postscripts, afterthoughts on section 5, which is where things peak out. And that will get us through the first third or so of the course, all of the background information necessary for the course. So there is section 4, and we'll go on into section 5 next time.